So I'm starting to record this meeting. Is it okay? So,
all right.
good. Any question before I begin? Homework is due Thursday, right? Thursday.
Yeah.
Okay, so today.
Actually, I have
Yes.
a question related to homework question number 2.
Sure.
Like plotting the graph of x2.
Right.
And what you are expecting exactly from that question is like the same thing, whatever we did for the coin toss?
Yeah, so for the coin toss, I gave you x1. X1, of course, can be drawn in many different ways as long as so what is coin throw? Coin throw, you can have two possible values, 0 or 1, right?
Yeah.
And 0 stand for tail, 1 stand for head, and then there was a 50% probability to be 0 and 50% to be 1. Therefore, I make the length of the 0 to be 1/2, length of the 1 to be 1/2.
Yeah.
But you can make many different ways to make the length of 0 to be 1/2. You can combine the two 1/4 into 1/2. So there are many different ways. But I gave you one example of x1. This is one visualization of the random variable x1. And then I want to create another random variable, x2, which is independent with x1. So the x, I mean, if without the independence, there's probably it's obvious how to do it. But if you want independence, then you need to make sure that all the events coming from this x2, which is the pre-image of 0 and pre-image of 1, has to be independent events from the x1, the one from the x1. So I'm not sure if I'm making sense. So let me. Okay, so let me share my iPad. Share screen. Okay. Okay, so here, so coin throw. Coin throw, another name is Bernoulli random variable, because Bernoulli random variable takes either two values, 0 or 1. So, and I chose my sample space to be simply 0 to 1. That's my choice. I chose my sample space to be 0 to 1. And I also chose my probability on the sample space to be just the Lebesgue measure. So the length. I chose whatever set has the probability measure given by the length, or more exactly, it's Lebesgue measure. So obviously, probability of the whole sample space omega will be 1. Length is 1. Okay, then I gave you one example of x1. x1 has 0 up to 1/2, and then 1 to 1. So here's the value 1. So that was my choice of x1. That's a random variable. And what's the sigma algebra generated by this x1? So maybe I will make this one also. Just to be perfectly rigorous, 1/2 doesn't belong to the bottom, but 1/2 belongs to the top. So any question about this definition? No. Okay, then what is the sigma algebra generated by x1? Sigma algebra contains, of course, null set, nothing, and the full set, which is 0 to 1. and what? Pre-images of x1, all the pre-images of x1. What is the pre-images of x1? Let me turn down the air conditioner first. Okay, any answer? What's the possible pre-images of x1? So all the pre-images of x1 have to be in the sigma algebra of x1.
0 to half?
Yes, 0 to 1/2, because 0 to 1/2 is exactly the pre-image of 0, right? That was
And a complement.
and the complement. That was pre-image of the 0 set, and the complement, which is 1/2
half to 0.
Great. There's nothing else needed, because this 4 element, you can check that it's closed under complement, closed under union. So it's sigma algebra. So that's the smallest sigma algebra, such that x1 is a random variable. Now we have to choose another random variable x2, such that if you find the sigma algebra here, this sigma algebra must be independent with the above sigma algebra. So you have to make sure that these two are independent. That's the goal. Then we can say that x1 and x2 are independent random variables. So we have to somehow draw x2 such that these two sigma algebras are independent. And one solution, there are many solutions because I created actually infinitely many independent random variables. But one solution was like this. So I will use the red. So one solution was like this. There was one possible way to choose x2. So in terms of this x2, the sigma algebra will be this one. And now, what is the preimage of x2? Preimage of 0 set. So for the x2 case, so here it was x1. But for example, x2 preimage of set 0 was these two parts, right? So this is 0 to 1/4 union 1/2 to 3/4. That's exactly the value that goes to 0. That's exactly the value that maps to 0 by x2, which means exactly the preimage of 0 set by x2. Okay. And then we also need the complements, because if there's any element in the sigma algebra, its complement must also be there. So complement is 1/4 to 1/2 union 3/4 to 1. And it turns out this complement is also the preimage of x2 of 1, right? So all the values here maps to 1 by x2. And this forms the sigma algebra. Again, you can check that it's closed under complement, closed under union, right? So these are also sigma. So these are x2. And now you can check that if you choose any element from the first sigma algebra, so any event from the first sigma algebra, and any event from the second sigma algebra, they are independent events, which means the two sigma algebras are independent. And that means x1 is independent to x2. Of course, you have to check this one. How to check this one? You just check all the pairs. Check all the pairs. Now, I think we did last time. But any question about this checking, how to check the pairs? What's the independent of the event? You just calculate the probability of the intersection of two events, and that has to be product of probability of each event. That's what you have to check. If that's true, then it's independent. The two events are independent. So that's the answer, how to find an example of the answer of x2. And now the homework was, I gave you this one as x1. The above is an x1. And I asked you to, so here, what's the sigma algebra? Sigma algebra is preimage of 1, preimage of 2, preimage of 3, 4, 5, 6. So those are 0 to 16, 16 to 26. Those are sigma elements of sigma algebras, and those complements and unions. So sigma algebra contains many elements. So we want to create another random variable x2, some graph such that this x2 creates another sigma algebra, which is independent with the sigma algebras on x1. Does it make sense? Anybody did this, had any progress?
No, still working on it, basically.
Okay. Okay, so let me talk about it after you work more, and after submitting the homework, maybe we have another time to discuss if it's not understood. So today I want to talk something else, but also fundamental, important. So let me start. So first, I will ask something from the analysis. So let's consider a sequence, x1, x2. Those are number, not very random variables. So consider infinitely many sequences. And let's say this sequence converges to certain number. So xn converges to a certain number a, let's say a, as n growing to infinity. So another notation for such thing was you learn in calculus that xn as limit n goes to infinity is a, right? And what you should, I want you to recall the epsilon delta definition of this thing. So we say, so what is the meaning of this? So you can say that xn is getting close. So an example is like 1, 1/2, 1/3. So that's the sequence defined by 1 over n, right? Sequence, right? And what is the limit of 1 over n? N going to infinity. As n grows, what is how this sequence converges to which value?
0.
0, yes.
Yeah.
So we want to, so we all know by intuition, but we want to prove this. We want to make it rigorous statement so that we can prove this and show to other people. And this is how we do it. So how to prove such things? So how to prove such thing? This means that, let me first write down in words, xn is getting very close to a as n grows. That's the statement, right?
Mhm.
But that's the human language. It's hard to prove with this one. So I can also change this very close to arbitrary close. That's more accurate way of saying instead of very. So what is the close? If the distance is 1 millionth, is it close? If the distance is 1 billionth, is it close? No, the closeness is if you choose give me arbitrary small number, I can make it even closer. That's the meaning of arbitrary close. So if you give me arbitrary small number like billion, one of a billion, then I can give you n such that the distance of xn to a is even smaller. That's the meaning of this. So for any small number you gave me, and this is often denoted by epsilon in mathematics. Arbitrary small number is given by epsilon. So epsilon, you gave me arbitrary small number, like 1 over billion, 1 over trillion, and then I give you n, large n. There exists, so this is the number that I gave you, let's say capital N, so this is a special number, such that the distance between xn and a is smaller than epsilon. Not just that, after capital N, it's all smaller because after capital N, it's getting closer and closer, which means if you're even higher value than capital N, so for any n higher than capital N, this is true. So if you give me some number 1 over trillion, then I can give you like capital N, maybe 1,000. Then x 1,000 is distanced only by epsilon from A. And after that, x 1,000, 1,002, all the x after x thousands is all very, very close. So it's all within the epsilon distance from A. That's the exact statement of this, this one. Got it? Okay, so now I'm going to define, so this is just the calculus preparation, but I want to now define a series of random variables. So let's say there are a series of random variables. What was series of random variables? Sorry. Yes. Okay. So now I will apply this knowledge to the series of random variables. So, let xn or xj be a series of random variables. So x1, x2, infinitely many are the random variables. Okay, and if I add, if I evaluate this random variable was a function that assign a number to each sample, right? Assign a number to each sample. So choose arbitrary sample we denote by small omega, right? This is a number, right? Then this is a sequence of number, as I just introduced it before. This is just a sequence of number. The sequence of number, because I fixed omega. So before was a sequence of function, but now it's a sequence of numbers. And this number may converge or not. This may converge or not, right? Okay, so let's combine all the points where xj of this sequence converges, which means has a limit. So you can find, so consider all the omega. So depending on the omega, you get a different sequence of numbers, right? So consider all the omega with such that this sequence has a limit, which means it converges. So that's the same thing as has a limit. So collect all such omega. Okay. Let's see. Let me slightly change here. Converges to. I will make this make it explicit. Converges to what? Converges to some. Exists some other random variable such that it converges to this. So let's assume omega is the point where xj of omega, the sequence of number, converges to x of omega. So this is exactly the same thing as limit of xj of omega. Omega is fixed, and j goes to infinity is given by x of omega. So find all the omega that satisfy this equation. Xj are given random variable, x are also given random variable. Okay. These are events, right? This is an event because it's a subset of the omega. Right? So we can measure the probability of such event. So if this probability, all the sample where this sequence of xj converges to x has the probability 1, if it has a probability 1, then we say, I don't have space. Let's move to the next page. Then we say that xj, the random variable xj, converges to x almost surely. That's the definition of important convergence property of the random variables. It's not just the convergence of a single point, single function, single number. It's the convergence of the whole function converges to something else. We saw this convergence last time when we throw the coins more and more and take the average of the this coin throw. So number of heads. The number of heads after we throw 10 times or number of heads after we throw 1,000 times, the average is getting closer and closer to the function 1/2. This is such example. So xj was the average, so example last time. So we have xj, which are independent Bernoulli random variable. That was the definition. That's the terminology for the random variable, which takes 0 and 1. Independent Bernoulli random variables. So that's a coin throw. So each xj takes 0 and 1. And then we count average number of heads. And for that, let's use the notation Sn. So this we define to be number of heads, which is this one, after n throw, and divide by the number of throws, which was n. That's another random variable, which is, I showed a picture, the ragged picture. Here, yes. This is what we draw for S3, right? We stop here, but I showed you a mathematical computation of higher value S10, S20, and so on, right? Okay, so this function is getting closer and closer to what? Function getting closer and closer to this dotted line. This dotted line in red, that's another random variable, which is just a constant function all through half, everywhere half. So it converges to this function 1/2. Sorry for going back and forth. So which means that this random variable, series of random variable, S1, S2, those things converges to random variable 1/2. Here I just write the number 1/2, but remember this means it's a constant function 1/2. So we can say that Sn converges to 1/2 almost surely. Actually, we will prove this one. So how do we know that this is almost sure? Okay. Is it still recording? Yes, still recording. Why this? Okay. So that's an example of almost sure convergence. So almost sure convergence is if you, for almost all the choice of omega, that's probability 1 here, probability 1, almost any choice of omega here, xj of omega converges to whatever the limit x of omega. That's the almost sure convergence. Okay, so we defined almost sure convergence. Okay, so let me I want to copy this one. So this definition of almost sure convergence. Okay, so let me repeat. So xj or xn converges to x as n goes to infinity, almost surely. And another way to write is on a dot s dot. So almost surely, if and only if the following is true. So that's the definition. Okay, so let's rewrite this one using the epsilon delta that we just discussed. So what this means? This means for any epsilon, there exists. So you gave me any small number, I can give you a big, large number n, there exists n, such that the distance of xn of omega from the limit is x of omega can be smaller than epsilon for all n after capital N. That's exactly the same statement. So, which means if, in a colloquial way, if n is bigger than some number, some number means this n, then xn of omega minus x of omega is less than epsilon. That's the same thing, right?
Yeah.
This is, so I'm just keep writing the sentence in the same meaning. I'm just rephrasing the same sentence, right? And I'm doing it step by step so that, and eventually I want to change the sentence into something that I want. And this means that if n is bigger than some number, and this we write in a different expression, this we write as eventually. Eventually means if n is growing enough. That's what I mean. So this so that's the terminology which is often used in probability. So let me rewrite it. So this inequality is true eventually. And eventually means this whole phrase, if n is bigger than some number, n is large enough. So eventually, if n grows and grows, eventually this will become less than epsilon. Okay. So I want to find what is the complement of the above. So what is the negation of this statement? So if eventually, so let's consider this set. How can we describe the complement of this set? So the point omega where xn is eventually converging to xw, x omega. How can we characterize such omega if xn doesn't converges to x of omega? And here is a clever way. So this means, so if you gave me any small number, some small number, I cannot give you any n. No matter how large the n is, xn is away from x by a certain amount. It cannot be close. So okay, so how can I describe okay, so let's okay, so we want to describe what is the complement of this set. So epsilon is fixed in this sentence. Yeah, but above here is for any epsilon. So for any epsilon. So for any epsilon. So here it's eventually for any epsilon. But here now I just bring this part here, which is for a fixed epsilon. So I didn't write the for any epsilon part. So I want to find the complement of this statement. What are, how can we say if something is not smaller than epsilon eventually? Which means that xn minus omega, xn of omega minus x of omega has to be bigger or equal to epsilon infinitely many times. It never ends. This thing has to happen. If this kind of thing is bigger than epsilon only up to 1,000, then after 1,000 it's less than epsilon, so it's eventually the above statement. So it should this behavior should not end in any finite n. This should keep happening for all the infinity of n. If it happens at 1,000, then sometimes at 2,000 it should happen again. Maybe after billion, it should happen once more. So this thing have to happen, keep happening for infinitely many times. It doesn't happen all the time, but it has to happen infinitely many times so that this doesn't happen. Okay? So this must happen infinitely many times. So that's called infinitely often. And this also used a lot, so we have the abbreviation infinitely often. So infinitely often, what's implied is infinitely often in n. So as n grows, it happens for infinitely often, infinitely many n's. Like eventually is also with respect to n. Okay, so here I introduce two more terminology.
But in second case, we have to fix the epsilon, right?
Oh yeah, here this is for a fixed epsilon. This is
because at a certain point it has to be fixed. Yeah.
Yeah, for a fixed epsilon. Okay. So I described above the important definition of almost sure definition. This definition, and that's written in terms of this. The definition is in terms of this statement that involves eventually. So certain statement eventually. So this certain statement eventually. And the complement of this statement can be written in terms of the infinitely often statement. Okay, so I introduced eventually infinitely often. And now, so we will describe one theorem that determine when when certain event is eventually true and when certain statement is infinitely often violated. So we will give a theorem about such thing. So any question up to here? Okay, so next. Maybe I will give an example. Yeah, let me give an example. So what I just gave is certain statement. So certain So let's say an is an. Okay, it's a certain state. Statement. Statement. How can certain statement? Okay, let's say there's a statement. Sequence of statement. That's ridiculous. That's sequence of statement. Okay, there's a sequence of statement, and statement n is true eventually. I want to consider this particular event. That's an event. Statement n is true eventually means that the statement will be true if small n is large enough. That's the E. And what we just showed that is that complement of such thing is exactly the statement n is not true infinitely often. That's what we just said. The event, the statement n is true eventually. The complement of that event is the statement n is not true infinitely often. Okay, actually, let's define. This is not the most typical way to describe these things. So let's define an to be the event that statement n is true. So now it's an event, it's a subset of the sample space. It's a more familiar object that we can deal with. And then we write in this way. So an eventually, that means statement n is true eventually. So that's our terminology. Statement n is true eventually. Means that statement n is true eventually is equivalent to, we write in this simple way. So an eventually. So our sample may belong to an, then the statement is true, or doesn't belong to an if the statement is not true, right? So our sample will belong to an eventually. That's the meaning. Okay. And of course, then an eventually complement will be an doesn't belong to an, which means belongs to an complement infinitely often. With an complement is also same thing as statement n is not true. Any question? So above here is to introduce this notation. So we just consider, so ANs are event, and AN eventually means that we belongs to this event eventually. If n is growing large, then our sample omega belongs to this AN. If that doesn't happen, if the complement of this event is our sample omega, small omega, belongs to an complement infinitely often. Good? Okay, so let's give an example. Let's choose the xn as a Bernoulli random variable. So our coin throw. Oh, no, this is not the correct spelling. Bernoulli random variables. and they are also independent. Bernoulli random variable with probability half. So exactly the coin thrower case, and independent. Okay, and let's define the set of events, sequence of events, to be where nth throw gives head. That's the event. Nth throw gives the head. Okay. Now let's calculate, let's consider the n eventual. N eventually means if n is large enough, you keep getting head. So after a certain point, you keep getting head. That's the an eventually. What will be the probability of such event?
That's the half.
Yeah, there's a chat. Oh, you gave two answers? No, 1/2. Okay. So what is the probability that eventually an means eventually you are getting head every time you throw? So first, x1 can be head, x2 can be 0, x1, 1, 0, but eventually you will keep getting ones. You keep getting ones all the time. Yeah, I'm suddenly blocked how to prove this. But what's your intuition? Let's just say the intuition. What is the probability that you're getting head? So after 1,000 throw, you getting infinitely many heads. So I mean, not infinitely many. You get head all the time. You throw infinitely many times, and you're getting all the time heads after like 1,000 throw. That's like eventually you're getting head all the time. That probably will be 0, right? That's too strange. You keep getting head infinitely for eternity. So if you keep throwing infinitely many times, you're bound to have head and tail mixed, right? So if you keep getting head after some point, then that's probably 0. Yeah, I'm having difficulty with how to prove. I thought I had an argument.
But we said that, like with law of large number, the probability of getting head or tail becomes equals to half, no? When we throw coins number of times,
right, exactly. So
yeah, if it was half, yeah, but it's saying like it should be 1, then it's very, very unlikely. So that's why we get 0 here.
Yeah, only by chances of getting only head is like likelihood is 0.
Yeah, even with a very biased plan.
Yeah.
Okay, your discussion went well? I think I didn't catch up.
Yeah, that's fine.
Okay. Yeah.
We try to understand what you are exactly, like saying here, because what you are saying is, like, what is the probability of, like eventually getting all heads, right?
Yes.
Yeah, that's gonna be, like unlikely. So it could be 0.
Yeah, unlikely. Right,
yeah.
Exactly. Unlikely. So it's 0. Yes. law of large numbers says that it's unlikely. I think we can prove this soon, but right now I'm having a difficulty. So which means the complement of this one will have, of course, probability 1. If certain event is 0, its complement will be 1, of course, right? And what was the complement according to the previous statement? It's AN complement infinitely often. Infinitely often, you will get tail. It's not all the time tail. You will get here and there tails, but infinitely often. It will never stop. And that's likely, right? That's very likely. You will keep getting tail at some point. That's one. Okay. Now I will introduce a theorem. I don't know why it's called lemma here. So Borel's 0, 0, 1 law. This is Borel's 0, 1 law. And this says that this particular event, AN eventually, or AN infinitely often, can only take the probability 0 or 1. It's an amazing fact. So let me state. So above is an example of Borel's 0, 1 law. So given any sequence of events, actually those events have to be independent events, but then this event AN eventually, here the example is only for the Bernoulli random variable, but for any random variable, for any event, any independent event, AN eventually has probability either 0 or 1. You cannot have any other value like 1/2, 1/3, that's impossible. That's the Borel 0, 1 law. And let me state, so if, so probability of AN, so AN is an event. If I sum this probability, sum this up, and if this sum turns out to be finite, then probability of AN infinitely often is equal to 0. This is Borel Cantelli lemma. And the other case, if, so here AN is just a sequence of events. ANs are sequence of events. Like AN is the events that nth row is ahead, something like that. Now let's consider the other case, probability of AN is infinite. Now let's say if it diverges, then probability of AN infinitely often is now become suddenly 1. Okay, here's a catch, a little details. Actually, this is not always true. The second one is not true. We actually need one more condition here. The second case is only if and if ANs are independent. So those events, these infinitely many events, must be independent set of events. Then probability of AN infinitely often is 1. So it's either 0 or 1 if the sequence of events are independent. And this is called the second Borel-Cantelli lemma. Unlike the first Borel-Cantelli lemma, second Borel-Cantelli lemma has this independence condition. Oh, actually, using this, now I can prove this previous example. Proof of previous example. Using this 0, 1 law. Okay, let's, so AN. What was AN in the previous example? AN is nth row is head, right? Nth row is head. So what is the probability of the event AN? AN was the definition, nth row, you get head. So 8,000 doesn't care about the first row, second row, but it means that if you, in the 1000th row, the particular row, you get head. That's the event 8,000, 8,000. So what is the probability of AN? Answer is very simple.
Could you repeat the question, please?
Yeah. Okay, I will repeat the question. So, so in the previous example, we defined AN to be the event where nth coin throw gives you head. So A1 means, so you think of coin throw infinitely many times. You will coin throw infinitely many times. And each omega gives you like one infinite sequence, like head, tail, tail, head, head, tail, tail, head, 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 tail. So this infinite sequence corresponds to a single sample, okay? And then if you pick certain sample, what is the probability that your 10th throw is head? What is the event that your 10th throw is head? That's represented by A10. So I'm asking probability of A10, which is, what is the probability that your 10th throw gives you head?
Half.
Half. Clear? Half for all n. Because AN only cares about nth throw. It's not affected by n-1, not affected by the what's after, because those throws are all independent. Good? Okay, so we obtained this one. So this means this is equal to what? Is it this case or this case? This or this?
I think this is the first case because it's the finite number of throw.
Oh, no, I'm just asking, of course, and this is not finite number of throws. So,
I thought it was the second case because
you just proved that P of AN is half for any n.
Okay, so then that should be the second case, yeah.
yeah, and it's also independent as well.
Then I asked this simple sequence, what is this? What is summation of n to infinity of half? This is just half plus half infinitely many times, right?
Mm.
So this is half plus infinity.
Second.
For this sequence to have finite sum, then this P of AN must getting smaller and smaller, not like the half all the time. So like a P of 8,000 is half, P of a billion is half, and then there's no way that this summation will be finite number, right? The summation will diverge. And according to the Borel's, actually the second Borel-Cantelli lemma, we obtain probability of AN infinitely often is equal to 1. So keep getting head infinitely often, not keep getting head infinitely often is 1. Infinitely often means you don't stop getting head at some point. You keep getting head off and on, but you keep getting head. You don't stop getting head at some point and just keep getting tail after all. Let me keep writing. So let me copy this one in the next page. Okay, so that's our application of Borel-Cantelli lemma. And what's this complement of this event? So what is the complement of so AN event? So I want to write what is the complement of this event. Complement of this event is eventually it's all the time not in AN, right? Either AN infinitely often or not AN eventually, right? So not AN means AN complement eventually. That's the complement of the above here, which I did here. Same thing.
Yeah.
And therefore, this will have probability 0. So one event has probability 1, then the complement will have probability 0. What does this mean? This is the tail. Tail eventually has the probability 0. That's what we just proved. Of course, in the example, we show that we guess correctly the probability of AN eventually, which is head eventually, is 0. Very unlikely to have head all the time after some point, right? But whether it's head eventually or tail eventually, that's of course same. So we just proved that tail eventually is 0. Using Borel-Cantelli, this can be proven. So similarly, probability of head eventually is also 0. So that's the application of Borel-Cantelli lemma. This unlikely thing we can now prove rigorously. And for that, we need to prove the Borel-Cantelli lemma, right? Okay, let's see if we can prove it in the remaining time. Proof of, I'm not sure, I don't think I can prove it both of them in time. Okay, so let's start. So probability of AN infinitely often. So what's the assumption for the first Borel-Cantelli lemma? Was the probability of AN, then from 1 to infinity is finite. That was the assumption. And using that assumption, we will prove that this probability of AN infinitely often is 0. That's the goal. We will show that this means 0. What is infinitely often means? So let me write in this way. So our sample this means that if you choose random sample, that then this belongs to this event infinitely often. So same thing. Choose arbitrary sample with small omega. What's the event? That it belongs to AN infinitely often, the same thing. Okay, so infinitely often means that, which means, now let's consider an union for certain. So consider this event. This is the event where you union a k plus 1, a k plus 2, all the way to infinity. So let me ask, if omega is a small omega belongs to AN infinitely often, will this small omega belongs to this set, the union? If the small omega belongs to AN infinitely often, the small omega will belongs to this union? That's the question. So for example, this union is like if the k is 100, then this is the union of 100, 101, 102, 103, all the way to infinity. Union of all of them. And if small omega has the feature that it belongs to AN infinitely often, then will this small omega also belongs to this union? That should be simply yes, right?
That's
this will be true, right? This will belongs to this union for any k, right?
Yeah.
For all k. So this two statement is same thing. This if omega belongs to AN infinitely often, then it belongs to this infinite union for any k. And actually, the opposite is also true. If omega belongs to this union for any k, then also omega belongs to AN infinitely often. Because you can make k arbitrarily large. You can start from a billion and 1, a billion and 2. And if omega belongs to that union, means that omega must appear in certain AN for n larger than billion. So if this is true for any k, then it exactly means the same statement. So this is the same statement, so I can change the expression. Okay. Okay, so now this is a certain event. Let's call this event BK. Let's call this event BK. BK is the event where omega belongs to the union of a k and above. Okay, and BK is monotonic. If k is growing, it's the union of smaller and smaller set, right? So BK is monotonically shrinking, which means BK includes BK plus 1, right? So it's BK for all k, but BK is shrinking, set, and for such shrinking set, there's a so this event is this bk for all k is belongs to this is the it belongs to B1, B2, B3, all the way to B arbitrary large number. So this can be written as the limit of bk, where k is to the limit, because it belongs to all the k's, all the bk's. And bk is the monotonic sequence. Now there was, so as, so, and then there was the continuity of the probability measure. So it will be given by limit of k going to infinity. That's the continuity of the probability measure. So if there's a sequence of monotonic sequence of events, then the probability of the limit, which is this one, will be the limit of the probability. Okay. And what is the bk? Let me write the bk. bk was, the definition of bk was omega belongs to this set. That was the definition of bk. So bk was this particular union of event. And the union of event, of course, it's smaller than summation of the probability of each event. Probability of each event is always, is a summation of probability of each event is bigger than the probability of the union, because some events may have overlap, right? Some overlap is double counted in the summation. Therefore, it's smaller than this. So, like this. And what is this? This one is the infinite summation after k, infinite summation after k. This is the full summation. This is the truncated summation. If the full summation is convergent, then this truncated summation, which is only summation of the infinite part, right? This infinite part must getting smaller and smaller if you start from the larger term. If you start from the later sequence, then those summation must getting smaller and smaller to 0. So this must goes to 0 because the original summation is finite, is convergent. So like 1 plus 1/2, okay, I think I have to finish. Again, the proof was a little out of time, but let's keep continue. So try to understand today's lecture and let's keep continue. Any question? So let me stop the recording and you can stop recording. How can I stop? Stop share. Stop share. Recording. Stop recording. Okay.